here where we have a frictionless movable piston here with a mass on top of it. We've got some, I'll call it H naught here for initial height. And then there's a mass up there. We are going to increase the temperature, which will expand the gas here, raising that piston up to some new height H. The height is 0.12 meters when the temperature is at 0. So this is 0.12 meters here with my initial temperature of 0 degrees Celsius. I'm just going to choose to call this initial with T naught and final with T this time. But you could use 1 and 2 again. You can use whatever you want for your notation here. So it's frictionless, meaning that when it's kind of raising up or down here, there's no friction from the walls. It's frictionless to move up or down here. Free to move up or down in that cylinder there. The block on top keeps the pressure constant. So we know we have constant pressure here. We want to find the value of H when the temperature over here is not unknown. I put a question mark here. If you know what this is 45 degrees Celsius. Okay. We also know that P naught, or P is just equal to a constant here. What's the value of H? That's what we're looking for. So we have a volume expansion here. This is not, and we have a temperature change. You might be thinking of thermal expansion like we had before. But this is an ideal gas. When you're dealing with the ideal gas problems, you know to apply that here right away. We have a few different situations though where things are changing volume or length. We had because of forces, because of temperature. Here we have ideal gas. Just make sure you can identify, which way to approach these. Here it's obvious, I think, if you're dealing with the ideal gas, how to approach it. You're always going to be using this right here to describe the change. And I'm writing this down in the 1 and 2 form like we used at the beginning, but I've chosen just T and T naught over here so we can change those variables here if we want to. Okay. But P is constant, so we can cross that off. This is really just V naught over T naught is equal to V over T with the initial final notation I've been using over here with those subscripts. Okay. The point I'm trying to make with the subscripts here is that this is really just arbitrary. If you want to keep it all 1s and 2s, and if you're thinking about that equation, then you would choose to define your variables over here that way. Pick whatever you like. Okay. We are looking for the height. I don't see the height in there. Where's it going to come from? Volume. So it's in there, I just don't see it yet. We know our temperatures here. We have something about the volume. How do I find the initial volume? What shape is this? How do you find the volume of the cylinder?
2 pi r height.
Not the 2 pi r, because we need pi r squared to get volume units of meters cubed. This would be pi r squared times H naught, I'll call it, for that original height. Okay. And don't get stuck here because you don't know the radius, just plug into the equation. This is this over T naught, this is pi r squared. Does the radius change?
No.
No, so we keep that r squared. Only thing that changes is the height. Divide by T. What happens with the pi r squareds? Those are gone. So we just solve this for H by multiplying up by T. Okay. What do I plug in for T naught? Can we divide by 0? So what's the problem?
Undefined.
That is undefined, that is the problem. So did I do something wrong over here? How do we fix that? do whatever we want, but what should we do? We can convert that, and we can do that, we can definitely use the equation to convert it. What should this temperature be in? This has to be in kelvins. So, this is obvious. If I give you 0 and you're dividing by 0, I'm trying to give it away, that you forgot to convert. If I made this 1 degree Celsius, you would not catch that. And you would see Celsius divided by Celsius, and you'd have meters, and you would feel like everything worked out fine. I'm not always going to give you 0. It's obvious here, and this is where you have to be careful with the ideal gas problems, is that we're not using the R that has the Kelvin in there, the 8.31 joules per mole per Kelvin, where you would see it when you plug it into the equation. It would feel like your units for Celsius would cancel out here and everything would work out just fine. The only way you know this is wrong is because it was 0. Okay? These have to be in Kelvin all the time. So this is, how many degrees Kelvin? 273, and what's this one over here? 318. Okay. Now we can do this by just plugging in the 0.12 meters times the 318 over the 273, and we'll get some height here for that H. And this is 0.14 meters for the H. Mistakes on ideal gas problems come in from things like this. You forgetting the temperatures here, that's a critical mistake. Forgetting to put it into kelvins. Sometimes people get mixed up with, volumes like this. They all start here. There's going to be issues with pressures, maybe being gauge pressures sometimes. Sometimes finding equations for your volumes, and be very careful about your temperatures here, because you just wouldn't be able to catch a mistake, I don't think, by looking at it, unless this was 0. And I have put a 0 on the exam before, but I don't always. And you're not always solving it this way, so it might not matter. But be very careful about your temperatures there. These problems on the exam, ideal gas problems, are usually not the hardest ones. They're usually not worth more than 10 points. These aren't very big either, just because they aren't that long. But just be careful with your units, and same thing with all of these. Volumes, everything. These have to be in the same units, these have to be in kelvins, keep everything in SI units, and temperatures in kelvins, okay? Before you leave, just look at the objectives here on this first slide if you still have them out. Number 8 on here, it says use kinetic molecular theory. That talks about the particles moving around and how it's related to temperature. That when you heat something up, it'll be moving faster, have a different kinetic energy. I'm not going to have us solve any problems on that. I'm probably not even going to talk about it any more than the few words I just said. For the purpose of the exam, though, you can cross that one off now. I'm not going to test you on that for the kinetic molecular theory. And I'll tell you next week, but there's a very good chance I'll end up crossing out number 4 also. But number 8, for now, we can cross that one off. We're pretty much done here. We are done with this first side of the objectives. The homework that I give you will have linear expansion, we'll have stress and strain, we'll have ideal gas on there. And I'll put some more up over buoyancy coming up the next day or 2 also. Okay, so get working on those things. The buoyancy homework, that first one is due on Tuesday. The next one will probably be due the following week. So there's still going to be another longer set of homework next week than what I'm giving you on the material today. This is kind of, these were different topics that I've included, but I think they were all fairly short, not very long problems, but next week there'll be some longer ones, so just be prepared for that. You can probably get all the homework that I put up for the stuff we did today done this weekend if you're caught up with this. Next